In this video, we are going to look at a very common algorithmic technique that is called dynamic programming. This is a technique used to solve recurrence relation in an efficient way. Okay, so by programming here, it does not mean coding. It is just a technique used to solve recurrence relation. In old days, solving this kind of problems, because a recurrence relation would have many repeating subproblems. So you don't, in order to avoid recomputing the same subproblems, you would use a table to record what has been computed. So the next time when you need to find the value of a subproblems that has already been computed, you just need to do a table lookup to find that value. And this method is called programming, or it's called dynamic programming. All right, so now let's look at an example. So we use DP to represent dynamic programming. Again, it is a technique for solving a recurrence relation. That consists of a lot of repeating subproblems. So the example we're going to look at is Fibonacci sequence f of I by definition. When I is equal to 1 or 2, f of I is 1. Otherwise, f of I is equal to f of I minus 1 plus f of I minus 2. So we could get an idea what it means by repeating subproblems by looking at the following tree. Okay, so let's say we have, so we want to compute f of I Okay, so in order to do that, we need, according to the definition, we need to compute f of I minus 1 and f of I minus 2. Okay, so now in order to compute f of I minus 1, you need to compute f of I minus 2 and f of minus 3. Likewise, if you want to compute f of I minus 2, you would need to compute f of I minus 3 and f of I minus 4. Okay, so as we can see here, these two are repeating subproblems in order to compute f of I, and this and that are also repeating. Okay, so that's, so then from this example, we know that in order to compute f of I, it involves several repeating subproblems. Okay, so that's what it means. So now let's look at a direct implementation of this function. So let's call this FIB of n. So we check if n is equal to 1 or n is equal to 2, return 1, otherwise return FIB of n minus 1 plus FIB of n minus 2. So that's straightforward. So of course, then we would really want to know how efficient this implementation is. Okay, so now let T of n represent the time, which means the number of steps it requires to compute FIB of n. Okay, so that means when n is equal to 1 or 2, it returns 1. So the time is a constant. Okay, so we use big theta of 1 to represent a constant. The reason for this is because you need to check to see whether n is equal to 1 or 2, and then return 1. So that is more than one step, but it is still a constant. Otherwise, we know that FIB of n is then equal to FIB of n minus 1 plus FIB of n minus 2. So for FIB of n minus 1, it incurs T of n minus 1 steps. For FIB of n minus 2, it incurs T of n minus 2 steps. So of course, after that, you need to add them up. So that you need a constant. So actually it adds 1 because you need to add them up. So that there's an extra 1 step. So then from here, we can see that we can first look at, because as we said earlier in the previous slide, that f n minus 1 actually is, you need this. Okay, so then you look at the time, T of n minus 1. It's, of course, it's then, it has 2 parts. One is n minus 2. The other one is n minus 3. Okay, so oops. So then, of course, this is positive. So this is greater than or equal to T of n minus 2. So this, okay, so that gives you T of n is greater than or equal to. So this is greater than or equal to T of n minus 2. So then it's greater than 2 times T of n minus 2 plus 1. So that's what we have. So then you, okay, so you use this equality. Okay, so again, so this is plus, so it is a constant, we just use 1, okay, because it is just 1 steps here. So then, so T of n minus 2, right? So we know that, so from here, so T of n minus 2, you replace n for n minus 2 here. And then this is n minus 3. This is n minus 4. Okay. Well, actually, we don't need that. So we just use this, right? So we will say this is greater than or equal to. So this is greater than or equal to. T of n minus 2 then is greater than or equal to. You repeat this, right? You replace n with n minus 2. Then this is n minus 4. So you replace this into here, okay? So then you do a little arithmetic. So you put, so this is equal to, this is equal to 2. Let me see. So this is equal to 2 to the 2's power t of n minus 2 times 2, because the 4 is equal to 2 times 2. So 2 goes in, so we get 2, and then plus 1. Okay, it's plus 1. So now we do one more step. So then you can see how we get to this. So now we get 2 to the 2. So got 2 to the 2. And then t of n minus 2 times 2 would be equal to t of t of n minus 2 times 2 minus 2. Now think of this as a whole n. So this is minus 2 plus 1. You have parentheses, and then plus 1. So you do arithmetic. So you put, so there's a 2 here. There is 2 here. So this is t, there's 2 here. Okay. Yeah. So you get 2 to the 2 to the 3, and then t of n minus 2 times 2 minus 2, that is equal to 2 times 3, and 2 to the 2 go in there, so that is 2 to the 2, and then still have 1. So 1 then is equal to 2 to the 0. Okay, so you think of this is your step, right? So that's this 3 is k, and then that's k. So what you are getting now is this. Okay, that's what we are getting. 2 to the k times t of n minus 2 to the k plus, so you add you add this up. So I think I forgot a 2 here. There's a 2 there. So that's 2 to the 1, and 1 there is 2 to the 0. So you got 2 to the 1 plus 2 to the 0. Okay, so then you write it up, then it would be 2 to the k times t of n minus 2k plus summation 2 to the I from 0 to k minus 1. So that's what we have. So now let's clear up all of these. So from here, so I want to know when is equal to 1. So when n is equal to 1 or 2, then it is equal to 1, okay, or a constant. So it just means that when n minus 2 to the k is equal to 1, let's say when it's equal to 1, okay, then it stops, okay? So because when that case, the t of 1 stops. So that means k is equal to n minus 1 over 2. So that's what we are having. So this part will become 2 to the n minus 1 over 2 times t of 1. T of 1 is 1, so we get that. All right, so think about this, think about that constant. Just 1, okay? Think about that. It's just constant, it really doesn't matter in this case, all right? So, so then when k is equal to this, so that means what? We need to change that. So that's when this stops. So that's n minus 1 over 2 minus 1. So that's really equal to n minus 3. So this is change this. This is not right. So this n minus, that's k. All right, k minus 1 is equal to n minus 3. So this would be n minus 3 over 2. But nevertheless, so we need something like this. So remember, you need you'll be very fluent on this summation. Let's say it adds up to L. So this is equal to 2 to the L plus 1 minus 1. Oops. I need to, so this is L. Oh. So this is L plus 1 minus 1. So then this summation is equal to 2 to the n minus 3 over 2 plus 1 minus 1. So then, of course, we know this would be 2 to the n minus 1 over 2 minus 1. So that is in the order of, so you add these two up, so it is in the order. So this 2 is in the order of 2 to the n minus 1 over 2. It is, of course, so this is really we can put a, so this would be a, so it's in there, okay? So this is means a smaller than 2 to the n, right? So it's greater than, so maybe it's convenient to write it as, so this is equal, so instead of, so we put an equal, and then equal 2 to the n over 2. So this is exponential time. Okay, so this is exponential time algorithm. So this is not efficient. So anything exponential, it's very inefficient because when n is not big, it will go exponentially bigger. So this is exponential. So for instance, when n is, now let's say 2 to the n over 2. So when n is equal to, let's say when n is equal to 40, right? Then 2 to the n over 2 is 2 to the 20. So that is 1 million. Okay, so this is it's a 1 million. So you know this is exponential, not good. So then we want to know whether we can do better. Well, it turns out, yes, we can do better. Okay. The reason we can do better is that this exponential blow up we just saw is due to significant recomputation of repeating subproblems. There are many subproblems that are repeated. As we saw earlier, there are so many. So then the way we want to do is to use a storage to remember, okay, what we have computed. So that so for a subproblem, so we computed it, we only need to compute it once, right? So remember earlier when we look at this FIB of n, we get FIB of n minus 1, FIB of n minus 2, and then this is Fn minus 2. See, if I computed this once, I store this value. I store this value somewhere, and then next time when I need it to do, when I need this value, I don't need to recompute it. Instead, I just do a table lookup. So likewise, so this is n minus 3. This also have n minus 3. So I store this. Next time I need it, I don't need to recompute it. Instead, I just do a table lookup. So table lookup is just one step. So that is the idea of dynamic programming. So this is not a very difficult thing. Okay. So now let's see what we are doing here. So we are going to use a array. So this is a one-dimensional array called Memo. So this stands for Memoize. Okay, so, and the idea then is we're going to use it to remember its value if it has been computed. Initially, its value is set to some value null. So this is upside down T means null or new. Okay. So this is, oops. New. This is in the terminology in circuit. Okay. So we are going to use a, so this is a memo. All right. And then let's say initially all of these will be new. Okay, it's a value. All right. All right, so now for a given value n, we are going to check. If it's not equal to nil, that means I have a value there. Okay, for instance, if this is n, it has a value there, that's not nil. That means it has been computed. So this subproblem has been computed. So what we need to do is simply return that value because it has been done. Otherwise, if n is less than or equal to 2, then we will set v to be 1 because that you are supposed to return 1. So that v will be placed in this array. And if if n is greater than 2, then you do fib of n minus 1 plus fib of n minus 2, whatever that value is, you are going to be placed into this. Okay, so now let me draw an idea here. So let's say my n is here. My n is here. And sorry, this is not the right way to write it. So let's say this is n. Okay, and the value, let's say, is nil here. So in this case, we're going to check. So let's say this n is greater than 2. So then, of course, we're going to compute fib n minus 1 and fib, oops, fib of n minus 2. So that means you're going to look at these two. Okay. So when they all have value, so suppose they have been already computed, right? So that means it has, so this has a value, this has a value. So you don't have to recompute it, you just do a table lookup, then you can do this, right? So that is the idea of, so this is called top-down approach. So this is top-down approach. And this is dynamic programming. All right. Okay, so we have seen an example. As I said, in reality, there are many recurrence relations when we write programs or when we design algorithms. So dynamic programming is a way to handle recurrence relation by using a storage. So DP is often used for solving optimization problems. To do so, first seek if we can devise a recurrence relation for the problem. So that's the first step. We can then use DP to achieve a faster algorithm. Faster means we're going to get a polynomial algorithm instead of an exponential algorithm if the following two conditions hold. Number one, the number of different subproblems is polynomial. So in other words, your recurrence relations only depends on polynomially many subproblems. Okay, so that means there are many subproblems. They are overlapping, they are repeating. Second, the optimal solution contains within itself optimal solution to the subproblems. Okay, so in other words, if an optimal solution involves solving subproblems, then the optimal solution, the part of the solution of the optimal solution also gives the optimal solution to the subproblems. Okay, so that's what the second conditions means. So when these two conditions are met, then we can use memoization, a storage space to record previous subproblems, okay, to store the values of previous subproblems to achieve a polynomial time algorithm. So this is shorthand for polynomial. Polytime means polynomial time. So then we are, so this is my way to handle dynamic programming. Okay, so I divide this method into two parts. Okay, so the first part is formulation. So what I'm going to do is first to interpret and formulate the problem by specifying a name for the problem, usually means the function name, and the parameters, where parameters represent the size of the problem, original and subproblems. Okay, so that is the formulation part. Localization is to come up with a recurrence relation. So for a given subproblem specified by parameters, we figure out how it is affected by smaller subproblems. So that's a recurrence relation. Also specified by parameters, express this dependency because the original problem depends on subproblems. So it is a dependency as a recurrence relation. Okay, so this localization part requires some analysis of the problem, and it is often the hardest part of DP. All right, so now let's look at a few more examples. So this is a rock cutting. Okay, so what you are, so let's look at the description of the problem. So the input is a rod of length n inches and a table of prices P from 1 to n listing the value of a rod of length I inches. Okay, so let's see what this means. Okay, so hold on a second. Let's see what this means. So this means this. So you have a rod. Okay. Obviously, let's say original length is n. And what you are given is the following price table. So let's P. So what you are having here is again, so this is up to, so starting from 1, 2, and n. So what that means here is that when, so for 1 inch, you can sell P1 dollars. Let's say this is, we just use dollars. So when the length of a rod is 2 inches, you can sell for money P2. And this is P sub n. All right, so that is what this input means. So you are given this table. You are given this table. All right. Okay, so what's the output? The output is I'm going to cut this rod. So I need to determine how to cut it in order to obtain maximum revenue, Rn. Okay, so this is my, because I don't want to sell the original rod, because you may not make the most profit. So I want to cut it depending on this table, Maybe just the original rod is already good, but it depends on the table. Okay, so so then use method I mentioned, formulation, and the localization method. Localization means finding out dependency. You can also call it dependency. Okay, so two parts. So formulation, we let R of n denote the maximum revenue that can be obtained. Okay, so I don't know what it is, but I just say, okay, this is what I want to find. So because you can only cut n, so this is, let's say we can only cut it into integral number. So the subproblems will be 1, 2, up to n, right? Because you don't need to cut it in this case. So that means you have n subproblems. So we want to compute out of n. So because you only have n subproblems, we know that we can get a polynomial time algorithm. So now let's look at the localization part. Okay, so let me bring up my drawing board. All right, so for a rod of length n, you have many different cuts, right? So you could cut it here, you could cut it here. So let's call this cut I. I don't know where it should be, but what I want to know is that if there's a cut at this part, then I have a rod of length I to sell, and the remaining one is n minus I, right? So that means I can sell this rod, this portion, that's length I, so that is P of I can sell this much. And then you can, for this part, maybe my drawing should be more, let's do it again. Okay, so let's say this is my rod length n, and then this is my cut I. I don't know where it is, so this I is from 1 to n. which means if it's equal to n, I don't cut it. If I is equal to 1, so this is 1 inch, right? So this I is from 1 to n. So when I fix this, I know for this I can sell P of I plus R of n minus I, because for the remaining part, that's n minus I, you can also cut it, right? So I don't know where to cut it, but I can just use R of n minus I to represent it. But I don't know where this I should be. So what I want is to get the most profit. So I want maximum of this, where this I is from 1 to n. When n is greater than 0, I can cut. Okay, hence that's what we get. So this is what we are getting. So when n is greater than 0, this is equal to this recurrence relation, otherwise 0. When n is when n is becomes 0, you don't have cut. So of course you cannot sell anything. There isn't any rod there, right? So that's 0. Right. So now with this, we can use memoization to record the results of subproblems. So let's call it cut rod. So this is a top-down approach. Again, we use a standard approach, memo of n. Initially, it's all equal to nil. And then for the given value n now, where I first check to see whether this memo of n is nil or not. If it is not nil, it's not equal to upside down t, then I simply return that value because now I have already computed it. Otherwise, we'll check if n is equal to 0, return 0, else, okay, we are going to find the maximum value. So this is a standard technique. So we first let v be 0, set v to 0. And then for I from 1 to n, because I don't know where the I is, but I will just check. So that will be the maximum of v plus, the maximum v or P of I plus cut rod P comma n minus I. So this is the recurrence relation. So it returns v, and that v will be placed in that position. So once this is done, it will be placed in that position. So when you go down here, so this n minus I is less than n. So this is a subproblem. Okay, subproblem. And it may have already been computed, or you may not, then you can just keep on looking at the previous value, okay? So that is the top-down approach using memoization. And the runtime, or the running time is, as you can see here, let's go back here. So for n, it depends on n subproblems, okay? And each problem also, for each I, it depends on I subproblems. So all together, it's equal to, so it will be, so I from 1 to n, right? So when I is equal to n subproblems. When I is equal to n minus 1, you have n minus 1 subproblems. So then the runtime is, okay, 1 plus 2 plus up to n. Okay. So let me do this better. Okay. So then, of course, you need to be very good at this summation. So this is equal to n times n plus 1 over 2. This is just in the order of n squared. Okay. That's the runtime. So we don't even need to look at this. You don't even look at this implementation. If you look at implementation, of course, you know it will be n squared. So i's from 1 to n. Each time you will need to look at. So if I is 1, you look at n minus 1 subproblems, right? So if n is equal to 0, you'll get no problem, subproblems. So it's still the same as earlier. Okay, so that is the runtime analysis. Now, speaking of now we have seen two summations. So these are important. So let me give you some idea how this is done. Oops. Okay, so what we are looking at is, so let me use this space here. So sometimes we need to add R 0 plus R1 plus R to the, let's say, K for R, which is not equal to 1, because when R is equal to 1, it's easy. You just K plus 1, right? Because R0 is 1, R1 is 1 because R is 1, so you have K plus 1. So if it's not equal to 1, how do we compute this? Okay, so let me tell you a quick trick. So I can just let S be the summation. I don't know what it is, but I can just say this is S. And then I'm going to multiply these equality, right? It's equation by R at both sides. So RS, that's left side. The right-hand side becomes 1 plus 2 plus RK plus 1. Now I can shift over a little bit. So this is equal to, or maybe you can imagine, I can, so this column, so let me just shift it a little bit, rewrite it. Okay, I'm gonna rewrite it here by shifting. Okay, so remove this now. So R times R0 is R1, so let's put it here. Times R times R1 is R2. And then R times R to the K minus 1 is RK plus R to the K plus 1. See, all of these columns are the same. So you subtract them, they cancel each other out. So what we are getting now is R minus 1S equals R to the K plus 1 minus R0. R0 is just 1, right? So hence, because R is not equal to 1, R minus 1 is not 0, so you can just move there. So that is the result. Okay. So this is called geometry series. The next one we're going to look at, as I said earlier, if you want to do this, 1 plus 2 plus, remember this trick, okay, because we use them quite a bit. So how do I do this? So I can reverse the order. It's still the same, right? So now each column, you add them up, it's equal to the same. It's all equal to n plus 1. So how many columns do you have? You have n. So that means you add them together at both sides. Left-hand side is 2s. The right-hand side is you have n columns. Each of them is plus 1. So S then is equal to n times n plus 1 over 2. Okay, so this is a easy trick. Okay, so in the earlier example, we figured out where to cut it. So, and we actually figured out the mode. Well, let's move back a little. So for this, we actually figured out R of n, the maximum revenue, but we don't. So for each time when we determine which one returns the maximum value, we need to record this. Okay, so that means that I know how to cut it. So that is constructing cuts. Okay, so we need to record or remember where we determine to cut. So then we need to use another array. So there's a C from 0 to n. So that C of n holds the optimal size I of the first piece of cutoff when solving is a problem of size j. Okay, so this is construction. So this up to this part is still the same, but now I want to know, instead of getting maximum, I want to know exactly when I get this I. So then, of course, I will check if V is less than P of I plus this. Okay, so that means this is greater than V. Then, of course, this is what I'm going to do it is to remember this I, and by making V bigger, and then remember this I by putting I into C. Okay, so then for this n, which is the input, because this gets, so you check all the possible value of I. Eventually, this is C indicates for this n, this is the location I want to cut to get the most profit. So then I put C into C of n to remember that cut place. Okay. All right, so that is rod cutting. So the next example we're going to get is coin collecting robots. And now let's look at the input. So the input here is M by N board with no more than one coin at each cell and a coin collecting robot in the upper level. Okay. All right, oops. And so each in each cell you have a point or you don't have a point, okay? And so let me just draw. So it's always a good idea to draw on a piece of paper. If you're very good at it, you can think of it in your mind, but it's always a good idea to draw it. So this is m by n, so you have m rows and n columns. And some of these cell has a coin in it, right? Let's say maybe there's a coin here, right? So let's say there's a coin, and the other part you don't. So so now here you can see you start from the upper left hand side corner. So this is where you start, okay? But then you just keep moving and then the robot should stop in this, the robot must stop in the bottom right corner of the board. So you must stop here, you start from here. There are some coins in here, okay? And the movements of the robot is subject to the following 3 rules. The robot must start in the bottom right corner of the board, as we always indicated, and then the robot can move at most 1 cell right. Okay, so let's say my robot's right here. The current robot, you can either move to the right, 1 cell right, or 1 cell down in a single step. And also the assumption here is that visiting a cell that contains a coin results in the robot collecting the coin. So let's say if there's a coin here in this cell, when you visit that cell, you collect that coin. So that's what this problem is. Then, of course, what you want to do is to figure out how this robot should move in order to obtain the maximum number of coins, to collect the maximum number of coins. All right. Again, let's look at this example, this problem. So we first, okay, use double C of ij. Now this has 2 parameters because it is a 2-dimensional board. Okay, so I and j denote the largest number of coins the robot can collect when it visits cell ij. It starts from the upper left corner, okay? And then when you are in there, that indicates, double C indicates the coin, the maximum number of coins it collects. Okay, so because you have 2 parameters, I can be from 1 to n and j from 1 to m. So all together, you have m times n many subproblems. So what I want to do is to compute CCM comma n because that's the lower left corner. So that's what I want to compute. So up to this, so far so good, it's not hard. So the second part is harder because we want to come up with a dependency or localization. By localization means I just isolate myself to only look at my current subproblems. Okay, so now we first look at the following. The robot can reach cell ij in one of the 2 possible ways. Oh, by the way, let me, maybe this will help you to think. So I have a board and I'm going to So this is 1, 2, 2n, and on the column, this is going to be 1, 2, up to n. So this is where I want to end up with. This is where you start. Okay. So let's say in here, this is i's row and j's column. So I want to know how I can end up with ij. So of course, you can, so it's either from top, right? So this is ij. So we can, no, it can either from here, oops, from here to end up. Let me do a better drawing. Oops, try again. Either from here, so which is I minus 1j from here, or from the left. So the cell here is I j minus 1. Okay. So either from top or from the left. So then I come up with a dependency. Okay, so we let Cij be 1. If there is a coin, because I want to count the number of coins I can collect. Otherwise, it's 0. Then for each ij, so now this I from 0 to m, j is from 0 to n. We're gonna, when either I 0 or j 0, that means it's off the board. So of course you can't collect anything. It's not in the board. Inside the board, I is from 1 to m and j is from 1 to n. So inside the board, so when I is greater than 1, greater than 0, and j is greater than 0, then it will be either from here or from here. So this either this or that. Which one is bigger? I need to choose. So for instance, if this is bigger, I want to go there. If this is bigger, I want to go there, then go into ij. So determining Cij, we know that if there is a coin, Cij is 1, otherwise 0. Okay, so that's how we come up with a recurrence relation. All right. Okay, so in this case, we use the same technique. We are going to use a 2-dimensional array because I want to remember the solution on this board. So everything else is more or less the same standard, right? So initially, each cell is set to nil. So for a given parameter ij, if it's not equal to nil, that means it has been computed. So then we simply return that value. Otherwise, we're going to check these 3 conditions. Right? So we're going to check this and that, this and that. We're going to check these conditions. Okay, so if I is greater than or equal to 1, that means greater than 0. Greater than or equal to 1, greater than 0. So if this is true, I return this. Else, if I is 0, return 0, or j is 0, return 0. You can say else if I 0 and j is from 1 to n, or j is 0 and I is from 1 to m, you return 0. So either way, but it's the same idea. So after that, you put v into ij. So return v. So the computing time is m times n because you have m times n many subproblems. To compute a subproblem, the dependency is constant. You only depend 2 subproblems. Okay. In the rock cutting, it depends if the parameters n, it depends on n subproblems. But this, no matter what the value of I and j are, it always depends only 2 subproblems. So that's a constant. So hence it's a constant of constant times m times n. All right, so next is to find the paths. We can work backward from cell m n. So from the lower right corner. So that means if memo, in this case, if this I minus 1j is greater than ij minus 1, then the path to ij came from above, okay? Because you have 2 ways to check. So this from above, this from the left. If this is greater than that, I want to go there. So that means I want to remember I need to go from there, from above. If this is less than this, that means it comes from the left. So I want to remember that. If they are both equal, then we just pick either direction. So it doesn't matter which one because they are equal. So then we can recover the path, okay, by using an extra, another 2-dimensional array in n plus n time, because you start from the lower bottom, and it's again drawings always helps. Okay, so you need to learn how to start from here. What you are going to look at is look at 2. So no matter how you end up with, you look at 2. Okay. So that means you don't have to look at all of them. You just, for each place you go, you look at the left, look at the. So the runtime is at most n plus m times a constant. So for this path construction. All right. So let me move. All right, so I will stop here and take a break.